Hello everyone. For today's tutorial video, I'd like to introduce the concepts of rotational motion, or motion that rotates around a center reference, rather than motion that exists only in a straight line path. Rotational motion is actually more complicated mathematically to describe than linear motion, not only because of the shape of the path, i.e. an arc or circle, but also because while with linear motion, you can assume it is only one object moving in a straight line. With rotational motion, it is actually many layers of the same object rotating at the same time, i.e. the point near the center will rotate at the same exact time as the point farthest from the center will rotate. Just like with linear motion, we have displacement to mean the change in position along a straight line path. With rotational motion, we have reference angles instead. So you will hear rotational motion also called angular motion for that reason. As you may already be able to imagine, a greater angle has a greater arc. So a 180-degree angle will have a greater arc circumference than a 90-degree angle. In particular, twice the arc circumference. And the radius of rotation will also affect the angle. So for example, with the same exact arc length, but a larger radius of rotation, i.e. a bigger circle, the angle will be smaller. As a bigger circle would logically mean that the angle would have to cover a larger distance. Stated in a formula, change in angle equals change in arc length divided by radius of rotation. And we can also see that the maximum angular displacement is 2 pi. As we know, the arc length of a full circle is its circumference, 2 pi r. And because angular displacement equals arc length divided by radius of rotation, 2 pi r divided by r is simply 2 pi. Although in your usual geometry classes, you are used to a full angle being 360 degrees, 2 pi is used in physics instead, because it is based off the arc length and radius of a circle, as shown. For that reason, that type of convention for a circle is called radians. So 360 degrees equals 2 pi radians, written rad for short. With the proof of how angular displacement works out of the way, we can move on to angular velocity, which is simply the technical formal name for the rate of rotation. Formally defined, angular velocity equals angular displacement over change in time, just like linear velocity versus linear displacement. Just like the angle is written with a Greek letter called theta, the angular velocity is written with a Greek letter called omega, which is different from the conventional English notation for linear motion to distinguish how they are two separate types of motion. On the topic of linear versus rotational motion, we can actually directly correlate linear velocity along an arc length by first noting that linear velocity equals change in arc length over change in time, as the arc is the linear path here. However, we also know from the geometric proof that change in angle equals change in arc length divided by radius. So we can isolate change in arc length by multiplying both sides by radius, and we get change in arc length equals radius times change in angle. We can then substitute this into the formula for linear velocity by stating that linear velocity equals radius of rotation times change in angle all over change in time, and that change in angle over change in time is the rate of rotation or the angular velocity. Therefore, we do another substitution and notice that the linear velocity along the arc equals the radius of rotation times the rate of rotation. Using my arm to demonstrate again, we can see that when I rotate relative to my elbow, that my hand travels faster along an arc path than the parts of my arm closer to my elbow. You can also notice this phenomenon in mechanical devices as well. So for example, a scooter or skateboard wheel will provide less linear motion than a car wheel owing to the differences in the radius of the wheels. In the context of rotational motion, linear motion along the arc is called tangential motion, and this comes from the geometric definition of a tangent being a point that intersects a circle at one point and no other. However, if we go back to remembering Newton's laws of motion, you may be wondering how rotational motion is possible, given that we know that objects want to stay in a straight line provided there are no forces acting upon it. The answer is a special type of force called centripetal force, which is what I will discuss in tomorrow's tutorial video. Don't forget to subscribe if you found this video informative, and make sure to see other tutorial videos, and follow me on either Facebook or Twitter for more content.